Hello everyone. In this video tutorial, we'll be exploring Milliequivalents calculations. One of the reasons it's important to be able to perform these type of calculations has to do with electrolytes. Electrolytes are extremely important because they support a number of vital functions in the human body, including nerve impulse conduction and muscular contraction. Now, while we get the electrolytes that our body needs from the food that we eat, there are several situations, for example, if a patient cannot eat, where you need to supplement the electrolyte requirements using intravenous fluids. And in fact, many of the intravenous fluids used in pharmacy practice do contain electrolytes. Electrolytes such as sodium, potassium, magnesium, chloride, and the like. How you do get these electrolytes is through dissolved salts, such as sodium chloride, magnesium sulfate, and the like. Now, when you have these salts and you put them in an aqueous environment like water, they dissolve, become ions in solution, and acquire the capacity to conduct electricity. So what the Millie equivalent allows us to do is measure the chemical combining activity of an electrolyte in solution. And to do that, it factors in the total number of ions in solution and the valence of the ions. Okay. So what I'm going to do is I'm going to show you a series of equations that you would need for this kind of computations. And then we'll look at some key examples of how to apply them. And by the time you're done with this tutorial, you should be really comfortable with this material of calculating Millie equivalents. First equation, the Millie equivalence is equal to the product of millimoles and valence. Now, if you really, truly understand this equation, that's all you need for this kind of computation. Okay. The other way you could rewrite this same equation is to have it expressed as the ratio of milligrams of a substance to molecular weight times the valence. These two equations are essentially the same. The only difference being the millimoles is now captured as a ratio of milligrams to molecular weight. It's also important to be able to compute milligrams when you're given molecular weight, and that's what this equation is designed to help you do. There are also many times when you also need to determine the concentration, either milligrams per milliliter or milliequivalents per milliliter, or some ratio of quantity to volume. And this equation allows you to do that. So why this is important is because you should be comfortable accurately interchanging the various units of dosing electrolytes. And the units of dosing electrolytes are milligrams, millimoles, and milliequivalents. So to move from milligrams to millimoles, you need the molecular weight. You divide the milligrams by the molecular weight, that gives you millimoles. And to move from millimole to milliequivalents, you need the valence. You multiply the millimoles by the valence, you get milliequivalents. You should be really comfortable accurately interchanging between these three units of dosing electrolytes. So now let's look at millimoles as a brief reminder. We'll also then look at valence just to bring that to the fore of your mind. And if you're really comfortable with this concepts of millimole and valence, simply skip to the various examples on calculating Millie equivalents that are shown in this video. First of all, let's look at millimole. Now, the millimole is simply a ratio of the number of milligrams of a substance to the molecular weight of that substance. So, by an equation, you have millimoles equals milligrams divided by molecular weight. What that means is it should be truly comfortable determining the molecular weight of a compound or a substance. And as a reminder, I list 4 steps that could guide you to calculate or determine the molecular weight of a substance. First, you need to list the number of atoms of each different type of element present in the formula, and then you look up the atomic mass on the periodic table, and then you multiply each atomic mass by the number of atoms in the formula. You add up all these numbers in step 3, and then you will end up with your molecular weight. So let's look at an example and see how we can bring all this together. It says, how many millimoles are there in 3.2 grams of calcium fluoride? We have our equation, millimole equals milligrams divided by molecular weight. So the first thing we need to do is get that 3.2 grams into milligrams. So we multiply by the conversion factor via 1000 milligrams in 1 gram, and that gives you 3200 milligrams. The next thing that we really need to do, which is not provided us explicitly, is the molecular weight of calcium fluoride. So the way we do that is you first need to know the molecular formula of calcium fluoride is CaF2. So 1 atom of calcium, 2 atoms of fluoride, the fluorine. Okay, so what you have here, and I put the subscript in red, that tells you the number of atoms. And then when you multiply that by the atomic mass, you will end up with the molecular weight. So 1 atom times 40, which is the atomic mass of calcium, plus 2 times 19, that gives you 78 grams per mole. But please note that since the weight is in milligrams, you want the units of your molecular weight to be compatible. So we're going to convert it from grams per mole to milligrams per millimole. Now, because there are 1000 milligrams in 1 gram and 1000 millimole in 1 mole, you will observe that the actual numeric value stays the same, but the units change. So we move from 78 grams per mole to 78 milligrams per millimole, and that's a useful trick to keep in mind. Okay, so if we do put that into our equation, we'll have 3200 milligrams divided by 78 milligrams per millimole, and that gives you 41.03 millimole. You should also be able to move from millimoles to milligrams, and that's what this example is designed to do. So here it says how many milligrams of potassium acetate are present in 75 millimoles of the substance. So we have the number of millimoles, but obviously we do not have the molecular weight of potassium acetate. Okay, so while this is the original equation, we will prefer it in a form where you rearrange and have milligrams equal to millimole times molecular weight. We know what the number of millimoles is. We do not know what the number of molecular or what the molecular weight is, so we need to determine that. So potassium acetate has 2 atoms of carbon, 3 atoms of hydrogen, 1 atom of potassium, and 2 atoms of oxygen. So you need to multiply the number of atoms by the atomic mass. So you have 2 times 12 for carbon, 3 times 1 for hydrogen, 1 times 39 for potassium, and 2 times 16 for oxygen. And when you add up all these numbers, you end up with 98 grams per mole. Like I said, you want the units of your molecular weight to be compatible with your quantities. So you have 98 milligrams per millimole following conversion. You put this into your equation, you have 75 millimoles times 98 milligrams per millimole, and that gives you 7350 milligrams. Very easily done. Okay, so now at least you're reminded on how to work millimoles. The next concept is to refresh our mind on valence. Okay, so when you're looking about the valence, or when you're talking about the valence, you're actually trying to basically measure the ability of an element to combine with other elements. And it is determined based on the number of electrons that will be added, lost, or shared if it reacts with the atoms. Okay, so without going too deeply into chemistry, I just want to show you how you can actually determine what the valence of an element or a compound is. So you have the 2 pieces that are really essential and pivotal for determining Millie equivalents. So one useful trick is the valence of an atom is equal to the number of electrons in the outer shell if the number is 4 or less. Otherwise, it's going to be equal to 8 minus the number of electrons in the outer shell. So what do these 2 last bullet points actually mean? If you take your periodic table and you actually looked at it and you went down the columns. So on this example where you see the numbers at the top 1, 2, 3, 4, 5, 6, 7, 8, those are the groups. Okay, so you have group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. And ideally, what you would find is all these elements want to behave like the group 8 elements. Okay, so they either want to behave like helium, neon, argon, krypton, xenon, and the like. Okay, because those are stable. Everything else is unstable. So what that means is, depending on where the element is, it will either like to give off electrons or gain electrons. So an example is lithium. Lithium has an atomic number of 3, which means it has one electron in the outer shell. It's a group 1 element. That's why it's a group 1 element. All the elements in a group have that number of electrons in the outer shell. So lithium has one electron in the outer shell. It would like to give off that electron and behave like helium. So you have an atomic number of 2. And because it likes to do that, the valence of lithium is 1. Okay, same thing with magnesium. Magnesium is a group 2 element. It has 2 electrons in the outer shell. It will want to behave like neon, which has an atomic number of 10. So magnesium would like to give off 2 electrons to behave like neon, and so the valence of magnesium is 2. If you look at an element that's like a group 7 element like chlorine, chlorine has an atomic number of 17. It would like to behave like argon, which is the noble gas closest to it. So it would like to gain an electron. So whilst it likes to gain an electron, to gain 1 electron, behave like argon, that means chlorine has a valence of 1 or minus 1, right? So this is one situation where the number of electrons of chlorine in the outer shell is 7. So it wants to gain 1 more to have 8. And then the total number, there will be 18, right? So that's a situation where it's greater than, your electrons in the outer shell is greater than 4, and so it would like to be 8 minus 7, which is 1. Okay, so the important thing is you should be comfortable determining the valence based on the periodic table or some previous knowledge that you do have. There are a number of examples that are commonly used, and for pharmacy practice or for the pharmaceutical calculations, typically you're dealing with valences that are from maybe 1 to 3. Hardly do you deal with anything more than 3, right? So what I show you here is some examples of some commonly used ions and their valence. And the message I have for you is, for this kind of calculations, we're looking at the absolute value. So chloride is an anion which is negatively charged. Potassium is a cation which is positively charged, and they all have a valence of 1. Potassium would like to give up 1 electron, whilst chlorine would like to gain 1 electron, but the valence is 1 either way. Same thing for calcium and sulfate. They have a valence of 2, and so on and so forth. So hopefully these have been some refresher for you in terms of determining the valence. Now, how do you use that information to actually determine the valence of a compound, for example? So here it says write the valence of calcium carbonate. So first you want to write out the formula and then write out a reaction for it. You need to have that equation, a reaction equation shown, a stoichiometric equation actually. So you have CaCO3. When you put this in water or in an aqueous environment, it doesn't stay that way. It dissolves and breaks up into these cations and anions. So you have a calcium cation, and then you have a carbonate anion. All right, so we know from the periodic table that calcium would like to basically give off 2 electrons, and so it has a valence of 2. And so to make sure that your calcium carbonate is electrically neutral, your carbonate also needs to have a valence of -2. For this compound, we are interested in the absolute value of either the cation or the anion. And in both cases, it's going to be 2. So hence, the valence of calcium carbonate is 2. Second example, it says write the valence of sodium acetate. Okay, so you put this in aqueous environment, it's going to dissociate. You're going to have sodium ion, cation, and then you have your acetate anion. Your sodium has a valence of 1, your acetate has a valence of -1, but we just want the absolute value of either the cation or the anion. Okay, and that means that our valence for sodium acetate is going to be 1 as well. Okay, so hopefully these examples illustrate the concept, and now you're fully armed to take on these Milliequivalent calculations. So first example, it says how many milliequivalents of magnesium sulfate, molecular weight 120, are represented in 1 gram of anhydrous magnesium sulfate. So this is a really straightforward example on how to work this equation. Okay, so we're going to use this equation where your millimoles is captured by the weight of substance in milligrams divided by the molecular weight. And the reason this is convenient is because you can see from the question that you have a quantity in grams which you can easily convert to milligrams. You've been given your molecular weight and you can easily determine your valence. Okay, so this is why this equation is really appropriate for this kind of question. So step 1, you would first determine the valence of the compound because that is not told you explicitly. And with time, you can just, by inspection, look and tell what the valence should be. But let's go through how it actually works. Magnesium sulfate, you put that in aqueous environment, it will break down or dissociate actually into magnesium, cation, and a sulfate anion. Magnesium with a charge of +2, sulfate with a charge of -2, which means that your valence for magnesium sulfate, which is the absolute of either the cation or the anion, is going to be 2. Step 2, you plug in the valence, molecular weight, and the weight in milligrams into the equation. Okay, so 1 gram is 1,000 milligrams, so that goes in the numerator. That's milligrams of substance. You divide that by the molecular weight. So like I told you, the units must be consistent. So you have 120 milligrams per millimole. And then you multiply that by the valence, which is 2. And so you have 16.67 milliequivalents. Very easily done. Okay. Next example. This is a little bit more interesting. Okay. And maybe typically what you may encounter. So it says Ringer's injection contains 0.86% of sodium chloride, 0.03% of potassium chloride, 0.033% of calcium chloride. How many milliequivalents of calcium chloride are contained in a liter of the injection? So this question actually is bringing together so many elements. You need to first be able to determine the quantity of calcium chloride from the percentage strength. And if you're not comfortable with percentage strength, I do have a video on that. You could easily check that or just brush it up on from some other place. So we first need to determine the quantity of calcium chloride from the percentage strength and then put that into the equation that we do have after we've determined the molecular weight and also the valence. So let's see how this really works out. Step 1. For this is our equation that we're going to be using, and we need to determine the quantity in milligrams. It's not given to you directly like the previous example. So we first need to determine the valence of the compound. It says calcium chloride, which is CaCl2. You put that in an aqueous environment, it's going to dissociate into calcium 2 plus and 2 chloride anions. So you need 2 chloride anions to have an electrically neutral calcium chloride. The charges must balance out. And so what we do see is the valence for this compound is going to be 2. It's going to be the absolute charge of your cation, which will be 2, or the absolute charge of your anion, which will be 2 times -2 absolute of that, which is still 2, right? So just take the one that's more convenient for you. So here it says your valence of calcium chloride is going to be 2. Okay, so that has been determined. What do we need next? We need to be able to determine the molecular weight in milligrams of calcium chloride in 1 liter. We were given the percentage strength, which is 0.033%, which means 0.033 grams in 100 milliliters. And so we can set up a proportion because a liter is 1,000 milliliters. And then we can determine the quantity that we need. So when we do determine the quantity, it gives us 0.33 grams. But we need the quantity or the weight in milligrams. So we multiply that by 1,000 milligrams in 1 gram. And we end up with 330 milligrams. Very easily done. So the third thing we need to do is determine the molecular weight of calcium chloride. And so now you should be comfortable doing that. You have 2 chloride atoms, 1 calcium atom. And so 1 times 40 plus 2 times 35.5 will give you 111 grams per mole. We need units that are compatible with what we're working with. So we convert to milligrams per millimole, and it's still going to be 111 milligrams per millimole. So let's summarize the key things that we found out for this example. We've determined the valence of calcium chloride, which is 2, the molecular weight of calcium chloride, which is 111 milligrams per millimole, and the weight of calcium chloride, which is 330 milligrams. Okay. So now we can substitute all this information into our equation, and that's what we're going to do in step 4. And we'll end up with 330 milligrams divided by 111 milligrams per millimole times the valence, which is 2, and we have 5.95 milliequivalents. So you have that much calcium chloride in the Ringer's injection 1 liter solution. So that's how all this thing comes together. Really easy, nicely done. Let's look at another example. This is a really interesting example. So it says how many milliequivalents are provided, how many milliequivalents of lithium, just lithium cation or lithium ion, are provided by a daily dose of 4 300 milligram tablets of lithium carbonate. And lithium carbonate has a molecular weight of 74. This example is really important because it allows you to use this equation. So this is one of those equations where it's more convenient to use the millimoles times valence directly. So you are going to determine the millimoles and then simply multiply that by the valence. So step 1, let's first determine the millimoles of lithium carbonate. Now, how do you do that? You need to understand that millimoles is equal to milligrams divided by molecular weight. Okay, so we're going to determine the millimoles of lithium carbonate and then use our stoichiometry to determine the millimoles of lithium ion. That's where we're going with this process, and then substitute that into the equation. Okay, so millimole here will be 4 times your 300 milligrams, so 4 tablets, each 300 milligrams, that goes in the numerator. And we divide that by the molecular weight, which would be 74 milligrams per millimole. And that gives you 16.22 millimole. This 16.22 millimole is the millimoles of lithium carbonate. But we don't stop there. We now want to determine the millimoles of the lithium ion itself. So we need to set up our stoichiometric equation as follows. So you have lithium carbonate, which dissociates into 2 lithium ions and then a carbonate anion. What that means is that the moles of your lithium ion to your millimoles of lithium carbonate, that's the ratio of the millimoles of lithium ion to lithium carbonate, is 2 to 1. The 2 comes from the coefficient in front of the lithium ion. And so we already determined the millimoles of lithium carbonate, and so we can determine the millimoles of your lithium ion. And that will be simply multiplying the 16.22 by 2, and that gives us 32.44 millimoles of the lithium ion. The valence is 1, right? So because the charge of lithium is just 1. So we simply put that into our equation. Milliequivalent equals millimoles times valence. And that gives us 32.44 times 1. And then our milliequivalence of the lithium ion is 32.44 milliequivalents. Really, really easy. Okay. Let's look at another example. And here what you're trying to do is you basically calculating, it says ammonium chloride molecular weight 53.5 is to be used as a urinary acidifier with a dose of 150 milliequivalent. It's asking you how many 500 milligram tablets should be administered. So this example is basically asking you to determine your quantity in milligrams after being given milliequivalents. So like I said earlier, you need to be able to accurately interconvert or interchange between milligrams, millimoles, milliequivalents. This one example where it's asking you to determine the milligrams given the milliequivalents. So we can use this equation where your milligrams equals milliequivalents times your molecular weight times your valence. From this equation, you know what your milliequivalence is. You know what your molecular weight is. So basically, we simply are required to determine the valence. We will determine the weight in milligrams and then simply determine how many 500 milligram tablets we need by proportion. So step 1. First, determine the valence of the compound because that's something that is not given us. So ammonium chloride dissociates to ammonium cation and a chloride anion. The charge there is 1, so we want the absolute value. So the valence of the compound ammonium chloride is 1. Very nicely done. Step 2. We want to plug the valence, molecular weight, and milliequivalents into the equation. So we have 150 milliequivalents times 53.5. The units must be consistent, so milligrams per millimole, and that gives us 8025 milligrams. But we don't stop there because you want to know the number of tablets which are 500 milligrams each to administer. So we determine the number of tablets as follows. One tablet is 500 milligrams and you have 80-20 milligrams, and that will give you a total of 16 tablets. So you see how all this comes together? Real exciting and real easy. Now in this example is one of those examples where you want to determine the concentration in milligrams per milliliter. Okay, so it's saying what is the concentration in milligrams per milliliter of a 10 ml solution containing 20 milliequivalents of potassium chloride. Okay, so that's where we use the last equation that I showed you on the very first slide. And this is the equation that you want to be using. So the first thing, or one of the things we want to determine, is the molecular weight. We want to determine the valence, and we need to ultimately determine the milliequivalents per milliliter to allow us to determine the number of milligrams in a milliliter. Okay, so step 1, we determine the valence of the compound. So KCl in solution dissociates to potassium ion and a chloride anion. The charge there is 1, positive 1 on potassium and negative 1 on chloride. But like I said, we want the absolute charge of your cation or anion. And so that gives you a valence of KCl being 1. So nicely done. The next step is you want to determine the molecular weight of KCl. So KCl is one chloride atom and then 1 potassium atom. So 1 times 39 plus 1 times 35.5. That gives you 75.5 grams per mole. And then you need it in compatible units, so that goes to 74.5 milligrams per millimole. The next thing we want to do is determine the concentration of KCl in milliequivalents per milliliter. That's the last term that we need. So you have 20 MEq divided by 10 ml. You have 2 milliequivalents per milliliter. So we now substitute that data into the equation. So you plug the valence, molecular weight, and the concentration in MEq per ml into the equation. And we have your milligrams per milliliter being equal to 2 MEq per ml times 74.5 milligrams per millimole divided by 1, which is the valence. And that gives you 149 milligrams per milliliter. So this is really simple how to determine milliequivalents, and I hope this video tutorial has been useful. If you have any questions, please send me an email mdankwa@csu.edu. That's MDANQUAH@csu.edu.